This is a time-lapse of a single-celled slime mold. As it searches for nutrients, it expands outward in a branching, highly efficient web. This pattern is mirrored in the Tokyo subway system map, one of the most complex human transit networks ever built. In 2010, researchers mapped the geographic locations of Tokyo's main transit nodes onto a petri dish using oat flakes. They introduced a slime mold and watched it forage. Within a few days, the organism connected the oat flakes, recreating the actual layout of the Tokyo subway. Human engineers spent decades debating, modeling, and tunneling to build this system. A brainless organism arrived at the same design solution, relying on the efficiency of biological growth. These transit maps are physical expressions of a biological self-optimization pattern. Network designers call this the Steiner tree problem. The goal is connecting scattered points with the shortest lines to central hubs. With 3 points, the math is straightforward. But adding dozens of locations creates complex permutations, making the absolute cheapest path a computational nightmare. Human planners solve this from the top down. They work with a rigid model of the city, prioritizing cost efficiency and direct routes. This efficiency creates a single point of failure. If one primary route breaks, the entire network can collapse. At the University of Toronto, researchers used a digital virtual slime mold to redesign the Toronto subway lines. The mold's algorithm balances construction costs against travel time and vulnerability, organically building redundancies into the web. By adding these biological safety nets, the mold's design proved 10% faster and 80% more resilient than the original human-engineered plan. This growth follows the invisible logic of fractal scaling laws, which dictate how a city occupies space as it gains population. Initially, a city expands in 2 dimensions to claim resources, mirroring a mold spreading across flat terrain. Eventually, the city reaches a density threshold. The research shows that going any wider would break the city into disconnected clusters, while going denser on a flat plane would collapse the road network. To accommodate more people without fracturing, the city shifts from a flat surface to a vertical volume. This transition triggers sublinear scaling, where a dense city requires fewer miles of road and infrastructure per person than a spread-out town. Within these 3D clusters, human interactions and the wealth they generate multiply exponentially. The heavy movement of traffic and people in a dense urban center functions like cytoplasmic flow, the process that pumps nutrients through a slime mold's veins. A vertical skyline is the geometric resolution to the physical limits of growth. Rigid street infrastructure often fails to adapt to organic human behavior, leading to chronic congestion. Biocomputational planning avoids this by using raw population density to determine exactly where resource nodes should naturally emerge. This method places services where people already gather, creating a 15-minute city where essentials are always within a short walking distance. Modern architecture is beginning to reflect this, merging structural engineering with the fluid behavior of moving populations. Managing a city as a living, computing organism allows it to evolve rather than stagnate. Our metropolises are giant colonies obeying the same survival algorithms found in the natural world. To see more, subscribe and follow our future investigations into the hidden geometry of the human environment and the biology of our cities.